Next process is called isobaric process. Okay, this is also thermodynamic process that occurs only in the constant pressure. So here you have to maintain the constant pressure. Okay, but other things that are volume, temperature, the net energy is not constant. It will be variable. Keeping pressure only is constant. Okay, so initially this is a container filled with the gas. Okay, this is a piston, is a movable piston. Place the masses on above the piston. Okay, when heat is given to the gas means it will be the temperature will be increased inside it, but keeping pressure is constant. Okay, so that the volume will be increases. Okay, so the expansion of the air is meaning of volume will be increases. Say initial volume is VA, final volume is VF, but pressure is constant. Okay, so in this process, so what do we have to find the water by the gas? Okay, so best example of this process. Okay, when cooking the food. Okay, so this is a diagram. It shows the isobaric process. In every day we are using that cooking the food in our kitchen is the meaning of isobaric process only. Okay, and the food is cooked in the open vessel. See, heat is given to the stove. Okay, so it will be burned. The temperature will be increases inside it, keeping the pressure is constant while the open the vessel. So here the volume will be expanding so that the deform will comes out. Correct. Here pressure is constant but volume will be increases when heat is given to the system. Okay, so this is the best example of the isobaric process. It's simple. No isobaric B, you put P in the bottom of the B, which means say BP means what? In generally pressure is constant. In isobaric process pressure is constant, so it is easy to understand the concept. BP like that, pressure is constant here. Okay, now we'll get the equation for the isobaric process and shows the button also. Okay, see the graphical representation of the isobaric process. So V in x-axis volume, pressure in y-axis. We know pressure is constant, so pressure is constant of both initial and final volume. So for a compression, volume will be reduced like this. So initial is here, final is here. For expansion, volume is increases. So put VA and VF here. Okay, in both the cases pressure should maintain constant, only changing in volume. Okay, now we'll explain this isobaric process in a mathematically. We get the some equations, from ideal gas equation. PV is equal to mu RT. In case of isobaric process, pressure is constant, so at a constant pressure, so we let as V is equal to mu RT by P. In the right side, okay, except temperature, okay, so all of the constant, that is mu or P are constant, so we let as mu is directly proportional to T. Okay, whereas mu R by P is equal to constant. So this is the relation between V and T in case of the constant pressure. That is the meaning of isobaric process. So bring that V in the right side. So we will write as T by V is also constant, which means the ratio of temperature by the volume. So we will write as the initial temperature Ti, final initial volume is Vi, is equal to final temperature Tf, the final volume is Va. So all are the constant for that isobaric process. Okay, already we see the graph also, the graph between P and V. So V in x-axis, pressure in y-axis. In case for the compression, volume will be reduced. So initial volume is here, say Vi, but P is constant. So P is constant here. So there is no changing in the pressure, same only, but we are getting Vf here. So this region is called work done by the gas in case of isobaric compression. It's called isobaric compression. In case of isobaric expansion, V in x-axis, volume, pressure in y-axis. Considering that initial volume here, because this expansion means volume will be increases, say Va, P is constant, then this is Vf. Okay, so this is the meaning of isobaric expansion. Okay, now we see that what is the work done by the gas during this process. Okay, in the formula for the work done, W is equal to integral of VI VF P into dV. This formula is very important. From the equation number 1, we know here P is constant, so take out of the integral. So W is equal to P into integral of VI VF into dV. Okay, so volume changes means both the integral derivatives are cancelled to each other. So we write as P into V upper limit then lower limit. Then substitute here, so we'll get as P into VF upper limit minus lower limit VI. So we'll write as W is equal to P. Then changing the final volume into initial volume means we write as del V. As del V means changing the volumes. Okay. Same time we will find out the work done by the value of pressure is constant, no? So W equal to P into del V. So del V, delta V denotes a change in the volume. Okay. If the value of del V, okay, become negative, del V is negative means VA is greater than VF. Okay. So W, if VA is negative greater than means the W also negative. W also negative, which means is the work done on the gas. Work done on the gas in case of the initial volume is greater than the final volume. Okay. If the value of del V became positive, work done also positive. In these cases, we will write as work done by the gas. Or then by the gas means final volume is greater than initial volume. Okay, so from the ideal gas equation we will write as the formula PV is equal to mu RT. Here pressure is constant, so taken here, so we will write as V is equal to mu RT by P. Okay, in case of initial volume means we put VA is equal to except temperature all of the constant, so write as mu R by P into Ti. Similarly, for the final volume, VF is equal to mu R P into TF. Okay. So we know the formula for the work done here. W is equal to P into VF minus VI. Okay. So we put this equation here. W is equal to. So what is the constant here? Mu R T. No. So we put pressure already. P is here. Then change in volume VF minus VI. Put VF is what? Mu R by P into TF minus VA means mu R by P into TF. Here mu P is constant, so taken out. So we will write as P into mu R by P into TF minus, so put TI. Okay, sorry, TI. And PP gets cancelled, so we have W is equal to mu R, then when the TF is common taken out, then we will write as 1 minus, there is no TF here, so we put TI by TF. So this is the formula for the work done in case of the Isobaric process. W is equal to mu R TF into 1 minus of TI by TF. Okay. So the graph shows that the work done of the Isobaric process. Let's see, here is VA, here is VF. So VF is increases means this is the water expansion. It's called Isobaric expansion at a constant pressure. Pressure is constant. There is no variation. Okay. So here is for expansion is work done is by the gas. If here is VF, here is VA means work done on the gas. Clear? For Isobaric expansion, work done by the gas. Okay. For Isobaric compression is work done on the gas. Okay. So we get the equation here for the internal energy from the first law of thermodynamics. Okay, you know del U is called internal energy is equal to amount of energy, temperature Q minus work done. You know W equal to P dV. So I put here. So that del U is equal to Q minus P into del V. So this is the formula for the internal energy in case of isobaric process. Okay. They will ask in the 3 mark question Okay, you studied all the things, definition of the thing, the formula, then graphical representation, then finding the work done. Okay, then internal energy. Okay.